Okay, so I think this is recording, and I want to go ahead and talk about the two linear programming problems, starting with this one that were on the review Monday that I said don't do these yet because we're going to look at linear programming later this week more specifically. So let's talk about this one. Things that I have told you about linear programming. The first thing that I have told you is that I usually start at the end of the problem. So this says blah, 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 blah. And then at the end it says, assuming you will answer all the problems correctly, how many of each type should you answer to get the highest scores? So that tells me two things. That tells me, first of all, this is what I'm trying to maximize. I'm trying to get the highest score. So I need to come up with an equation, excuse me, an expression really, that explains the score. In other words, something that if I knew how many of each type, I could plug it in and figure out what my score is. The other thing this part tells me is what is being asked for. And the how many of each type tells me that what I'm being asked for is how many of each type of problem I should answer on this quiz. So an algebra quiz consists of computation problems and graphing problems. So that tells me what my variables are going to be. So computation problems, I'm going to call X, and graphing problems, I'm going to call Y. So technically, really, the X stands for the number of graphing problems, excuse me, the number of computation problems, and the Y stands for the number of graphing problems. And if I knew that, then I could plug it into my objective function, which is going to be a function that tells me the score, in order to figure out what my score is. So now I need to figure out what that function is. Like, how would I figure out the score? Well, computation problems are worth 6 points each. Graphing problems are worth 10 points each. So if I knew how many computation problems I had done, I could do done correctly, I guess, I could do times 6 points. And if I knew how many graphing problems I had done correctly, I could do times 10 points. So that's going to tell me the score. And that is my objective function. So 6 points for each computation problem plus 10 points for each graphing problem will tell me my score. So that's how I would figure out whether or not I had got what score I had gotten, basically, to figure out what the highest is. Okay, now the rest of the problem is going to give me these inequalities, or they're also called constraints, that this part is asking for. So we've already figured out what we needed to figure out from the first two sentences. Next, we have you can answer a computation problem in 2 minutes and a graphing problem in 4 minutes. You have 40 minutes to take the quiz. So computation problem, oh, that's a little dark, isn't it? Computation problem in 2 minutes, graphing problem in 4 minutes, and we have 40 minutes to take the quiz. So that sounds like a limitation. And a limitation is what a constraint is all about. Like, that's the longest I can take. That's the greatest amount I can have. So I have to have less than or equal to 40 minutes taken. So computation problems, which are X, 2 minutes times the number of those I have, plus 4 minutes times the number of the graphing problems I have, has to all add up to less than or equal to 40 minutes. Okay? Then our next sentence says, you may choose no more than 12 problems to answer. Okay, so that's a total. Very often in these, you'll have at least one sentence or constraint that talks about a total. And a total means, total number, how many altogether. So together, up to 12 problems is what I can answer. So again, that's another limitation. Together, the number of computation problems plus the number of graphing problems has to total less than or equal to 12. All right, those are my only constraints, but I know, and really I have the hint over here from the graph, that I can't have any number, a negative number of computation problems or a negative number of graphing problems. So I know that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. So there's my 4 constraints. And we really usually have 3 or 4 because we're going to end up, when we have them all drawn, having either a quadrilateral or a triangular region. Okay, so next thing I have to do is graph these. So if I'm going to graph these, number one, I know that both of those are going to be solid lines because they say or equal to. So I have to graph these lines. So I don't have to worry about making them dashed, but I do have to worry about where they are. So I'm going to take the first one. And one way we sometimes graph is slope-intercept form, but the way we've been doing it mostly with these is finding the x and y intercepts. Meaning the x-intercept is where I plug in 0 for the y, which means 2x equals 40, x equals 20, and that this point is on my graph. The y-intercept is where you plug in x for 0 for x. So if I put a 0 here, this whole thing goes away. I get 4y equals 40, and y equals 10. So this point here is on my graph. Okay, I'm not going to graph that just yet because I have to figure out the scale for this graph myself, and I want to make sure I know what all I need to put on there because I still have another equation. So here's the other equation. This one's going to be an easy one to figure out with the x and y intercepts. Okay, when I plug in a 0 for y, and you could do this over here too, it's like that just goes away. The y part goes away. So x equals 12. So this point is on my graph. And when I plug in a 0 for x, same thing happens. Y is 12. So this point is on my graph. Okay, so one line goes between these 2 points, one line goes between these 2 points. And each of those I have to decide what to shade after I draw the line. So the points 20, 0, 12, 0, 0, 10, and 0, 12. So let's see what I want to do here. I could go by twos. I could also have a cat climbing all over the place, so excuse that. I could go by twos here and get up to 20 with no problem. So I think I may do that. I don't know. Maybe I want to go by ones. So the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, let me just make one more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I'm going to go ahead and go by ones. So this would be 20, 0 right here. And then the other point I need is 12, 0. So that's the x-intercept for the other graph. And really, I don't usually graph them both at once, but I just was on the x-axis. And then let's go ahead and finish graphing this one. The y-intercept is 10. So up 10. So there's 0, 10. So this is the same line that also has the 20. So I'm going to go ahead and draw that line. And like I said, it's a solid line because it's or equal to, not dashed. And then I have to decide whether to shade above or below it. A lot of these problems are below, but we have to make sure less than or equal to is generally going to be below. But if you don't know where to shade, what you do is pick a point and plug it in and see if it works. So like I could pick, there's a point 12, 0. That's below this line. Let's plug that point in. 2 times 12, that's 24, plus 4 times 0, that's nothing, is less than or equal to 40. Is that true? Is 24 plus 0 less than or equal to 40? Yes. So that means this is the side of the graph to shade, the side that has this point. Okay, so I'm going to shade in orange below that line. And you don't have to pick the point 12, 0. I just picked it because it was looking right at me. Okay, now the other line has 0, 12 as its y-intercept. I put it a little too high there, sorry. Excuse me. 0, 12. And then I need to connect these. Okay. And again, this is shaded below. Where is x plus y less than 12? Cat alert, excuse me. Okay, I'm trying to get him to move, and it's not working very well. There we go. Okay, where is x plus y less than or equal to that? Well, when x values are smaller than that and y values are smaller than that, like here, 0, 0. If this is the point 0, 0, 0 plus 0 is less than 12, so that point should be shaded. So yes, it's going to be shade below. And let me see what I can find in terms of highlighter that fits well. Most of my highlighters are kind of dark. But, so again, it's below. And there we go. Now, the line x is greater than or equal to 0, or the line x is equal to 0 is the y-axis, and it's greater than or equal to 0 to the right of that. The line y is equal to 0 is the x-axis, and it's greater than or equal to 0 above that. So the place where all of the shading kind of meets is right in here. This little quadrilateral area. Okay, so this little quadrilateral area has 4 vertices. 1, 2, 3, 4. 3 of them we know. 1 of them we don't know. That's the one we're going to have to find. And very often the one where the 2 lines meet is the one that you don't know just off the top of your head, and you have to find it. So I'm going to have to take these 2 equations, and basically I can treat them like equations because I don't care that they're inequalities. And I'm going to solve the system of equations for those 2 equations. Back when you first learned how to solve systems of equations in Algebra 1, and then we also did that in the fall, there were 3 ways to solve a system of equations in 2 variables, which is what this is. One was graphing, one was elimination, and one was substitution. Well, the problem with graphing is what you can see here. I could guess where that is, but it might be off slightly. How do I know if that's 4.1 or 4.2 or 4? That's the problem with graphing. So most of the time, to be accurate, we use elimination or substitution. Elimination is where you make the coefficients of either both of the y's or both of the x's, you make them opposite numbers so that when you add them top to bottom, it cancels out. That's elimination. Substitution is where you take one of the equations and get one of the variables alone and then plug it into the other one. I think I'll do that this time. This would be a good one, honestly, for either way. So I'm going to take one of the equations where it looks like it would be easy to solve for one of the variables, and it is. Now I've got one of the variables alone. So x is alone, so I have an alternate expression for x in terms of y. Instead of writing an x in this other equation, I'm going to write 12 minus y. I'm going to plug it in right there. So 2 times 12 minus y plus 4y equals 40. So 24 minus 2y plus 4y equals 40. 24 plus 2y equals 40. 2y equals 16, subtracted 24 from both sides, and y is 8. Okay, so the y coordinate of this point is 8. Now to find the x coordinate, if we use substitution, we have a very easy place to plug it back in. We have a place where it's just set up to find x. So I take this y and I go up here and I say 12 minus 8 is 4. So x is 4. So this point must be the point 4, 8. And there we have it. So determine the vertices. Now I have all 4 vertices. So 0, 0, 0, 10, 4, 8, and 12, 0. Substitute the variables. Now, the key thing here is this. Excuse me. I got a very good question today on this from somebody in our Zoom. And that was, how do I know when I'm supposed to plug in the corners, and how do I know when I'm supposed to just randomly pick a point in here? On Delta Math, When I gave you problems similar to this for Delta Math doesn't have any linear programming problems. It doesn't have problems like all of this. So all I could let you practice on Delta Math was just the graphing part, and that is just graphing a system of inequalities. So it's almost like this just came out of nowhere and you just learned to graph it. So on Delta Math, when they asked you to give a solution to it, all of these, everything that is shaded green is technically a solution to this problem. Meaning if I randomly pick any point in here, for instance, this point right here, 1, 2, 3, 4, X is computation problems, so 4 computation problems and 1, 2, 3 graphing problems. So that would be a possibility. That would be something that fits all the constraints. I would have enough time to answer 4 computation and 3 graphing problems. That's enough. That's 4 computation and 3 graphing is 7 problems, so that wouldn't be too many problems to answer. That wouldn't go over the 12 problem limit. That would be okay. It would fit all the constraints I have. But with linear programming, we're looking for more than that. We're looking for a specific objective, okay? And our objective is to maximize our score in this case. A lot of times it's profit. And it turns out that if you graph a system like this, the most special answers, the answers that have special significance, like for instance, the maximum numbers and the minimum numbers will always happen at the corners. So if I'm trying to maximize or minimize something, then I'm only looking at the points at the corners and trying those. Okay, so I'm going to take all 4 of those points and plug them into this. And I'm going to do it up here because I have some extra space here. So 0, 0, I totally know already that answering 0 questions of each type is not going to give me my max score. So that's kind of a gimme. All right, if I answer no computation and 10 graphing problems, I will get 100 points. If I answer 4 computation and 8 graphing, I will get 104 points. If I answer 12 computation and 0 graphing, I will get 72 points. So here's my maximum score. All right, so how many of each type of question should you answer to maximize my grade? I should answer 4 computation and 8 graphing problems. 4 computation, 8 graphing. What is the maximum grade I can make? 104.